Okay, like that, we have an idea, like what is basically C, where it is used and all. Okay, so before starting with the actual program, we should have all the basics. Okay, like the keywords, where all it starts using. Like it starts with the data type. Okay, like we have to see all those things one by one. So before that, even we should know how the things are going to get stored inside the memory, or like basically everything, like everything inside the system. Like when we speak about the computer, everything in it will get stored as numbers only. So conversion from one number system to another, that is a very important thing. Okay, like how it is being converted, like one number itself. Okay, like how it can be represented in different number systems. So number systems, while speaking about the number systems, what exactly it is, or how many types are there? Okay, how can we easily do the conversion order? We will see one by one. So even that is important. Maybe like you might be thinking why the number systems order we have to study now. No, it's not like that. It has like it has so much of importance. Okay, so as of now, please understand. This is in fact to understand the storage of the data inside the memory and all. This is actually important. Uh, no, usually I won't give the solution for that. That is for the practice purpose. If you cannot find the right answer, or if you like I told, like in yesterday's class I have told like how to try with your logic. Okay, so like I have shown in the class, recreating the pattern and all, like how I have done, you can try it in the same way. Like in the same way, you can just try it. If it's working fine, then no need to submit anywhere or something. If you're stuck somewhere, then you can send me the logic that you have written. You can just reply to in the discussion forum itself, and then you can like where you're stuck, that you can point out. Okay. Apart from that, you don't have to submit the classwork anywhere. Classwork is only for the practice purpose. Well, so whatever we have completed till there, do you have any doubt before going with the number system? Do you have any doubt in whatever we covered till now with respect to any of the topics we covered? No doubts. Others? Could you please respond? Attendance, don't worry about the attendance. I'll update it. Okay, I'll check the attendees list and update it for the till the yesterday's attendance. Okay. Today, anyways, I'll give some more time to mark the attendance. Don't worry. So, well, we'll start with the number system. So basically, there are like based on the number of what exactly the digits used or the base. Okay, the based on the base of the number system, there are four different types of number systems. So first type is nothing but the decimal numbers. Okay, decimal numbers. It has the base. Okay, base of what is the base? Do you have the idea? Base is nothing but 10. Okay, which means we are going to represent any decimal value using the digits from 0 to 9. Okay, using this we are going to represent all the decimal numbers. Then the second one is like the binary. So binary in the sense that the base is 2. Okay, which means we are going to use 0 or 1 to represent any binary value. Then the third one is nothing but octal. Yeah, the base is 8. So base is 8. That actually means we are going to use 0 to 7. Okay, so 0 to 7 are the digits used to represent any octal value. Then what it is, the last one is hexadecimal. Base is 16. Okay, and there we are going to use 0 to 9 digits as well as the alphabets or the characters A to F. Okay, so these are the things what we are using. This we are going to represent any number. Okay, now the thing is like we will go with the conversion from decimal to binary, decimal to octal, decimal to hexadecimal, then binary to decimal. Like that, we will convert from each and every number system to the other. Okay, so first one, I'll go with decimal to binary. Decimal to binary, I'll take an example of 125. 125 in decimal, we have to convert that to the binary. So basically what we have to do, if you want to convert that, like decimal has, what is like, we have the basis 10. Okay, so we are going to convert to the binary. So one number is being converted to the binary. Binary has the base 2. Okay, so we are going to divide this 125 by 2 by the base of binary. Okay, so 125 should be continuously divided by 2 unless we get a, or unless it's no more divisible by 2. Okay, so so dividing by 2 continuously, so 125 divided by 2, we'll get a 6 and 2. And the remainder 62. Yeah, the remainder we have to keep it aside. So that is 1. Then 62 divided by 2, we'll get 31. So again the remainder is 1. Then dividing by 2, we'll get the 15. Remainder is 1. Why 0? Okay, 30. Sorry. Okay, correct. So now 15 by 2, we'll get a 7. 7 and the remainder 1. Then 7 divided by 2, we'll get 3 and the remainder is 1. Then again divide by 2, 2 ones are 2 and the remainder is 1. Okay. So now this is what we have got. Now how to view this one. So how to consider this as a binary. So this remainder is what we are going to consider as the binary. Okay, so it will be like from the bottom to top. We have to consider that in this manner. So 125 in binary, what we have got is nothing but 1111 101. 1111 101. Okay. So that's nothing but 111101. So that is the equivalent binary. So that is the conversion from the decimal to binary. So to which number system are you converting? That one's base should be taken, and you have to divide the decimal number with that base. You will get the, so in this case, we have to get the binary. That is done. Now the second conversion is from decimal to, okay, let it be there. We will convert it back, binary to decimal. How to do it back? Okay, so binary to decimal. So I'll consider the same thing to convert it back to the decimal. So that's like 111101. If we have to convert this to the binary, sorry, decimal, what we have to do in the sense, we have to multiply. So conversion to the binary, we did the division. Converting back to the decimal, we have to do the multiplication. Okay, so from where we have to give the, or with what we should multiply in the sense. So these are binary digits are in fact known as the bits. Okay, so this bit is having the index as 0. Okay, this bit is the first bit. Okay, so starting from this right hand side, you have to count 0, 1, 2, 3, 4, like that. Okay, so you have to do it as, yeah, you have to multiply it with 2 power 0, then the whatever is the bit position, with that you have to multiply. So that into 2 power 0. Okay, that is getting added with the next one. So that is next one is 0. Okay, so the two for the bit position 1, the bit is 0, so you don't have to add that. Anyways, that is 0. So then the next one is 2 power 1 is done with the 0, then 2 power 2. So into 2 power 2, like this you have to do till the this one. Okay, 2 power 2. So 2 power 5 and 2 power 6. Okay, so wherever 1 is there, you have to just multiply that 1 with the 2 power value, 2 power bit position. So that is like 2 power 6, 2 power 5 plus 2 power 5 plus 2 power 4 plus 2 power 3 plus 2 power 2 plus 2 power 0. So what will you get? So what will you get as the answer here? Second from last 2 power 1. No, 2 power 1 is actually 0. Okay, so 0 into 2 power 1, I'm not writing it. Even if you write that will be 0. Adding the 0, it's the same. Okay, so when you add this up, okay, what will you get is nothing but back to 125 in decimal. Okay, so this is how you will get the binary, like binary to decimal, or the decimal from the binary number. Okay, that is 125. Now the next one is, so the first two, like this is done. Now the decimal to octal. So that's the third one. So I told when we have to convert decimal number to one another number system, we have to divide that with the base. Base of the octal is nothing but 8. Okay, so if I'm taking the example as 212, okay, 212 in decimal need to be converted to the not binary octal. So we have to do the division in a similar manner. So 212 divided by 8. What will we get? So 8, 8 2s are 16, then 8 6 are, yeah. And the remainder will be 4. Okay, then again dividing this with 8. 8 3s are 24. And the remainder is 2. So that's it. So this is now more divisible by 8. Okay, so we can stop that there. So now we have to again see that in the bottom to top approach. So 212 in octal is nothing but 324. Okay, so 324 is the converted value in octal. Now octal to decimal. Okay, so again it will be with the base of that particular number system. From where to where you are converting. Again, that base of the number system is taken. So octal to decimal. Sorry, octal to decimal. Octal to decimal. So again, I will consider the same number like 324. Like we'll see whether we'll get back the same. So we have to consider from this is the octal digit 0, octal digit 1, octal digit 2. Okay. So we have to consider the same for the calculation. So 8 power 0, 8 power 1, 8 power 2, like that you have to do. So the first one, so only 3 digits are here. So 3 into 8 power 2 plus 2 into 8 power 1 plus 4 into 8 power 0. Okay, so do we get it as 324? So 3 into 8 power 2 and 2 into plus 2 into 8 power 1 plus 4 into 8 power 0. Okay, so we will get it back as 2, 1, 2. Okay, so 324 in octal we have converted that to the decimal, that is 212. So when we sum this up, surely that will be 212. Yeah. Okay, so that's the thing. So that is the second type of like decimal to octal and octal to decimal. Now the next one is decimal to hexadecimal and back to decimal. So we will consider a number. So again, from the decimal, we have to convert to hexadecimal. So I'll consider the number like 472 in decimal. I want to convert this to the hexadecimal. So the base of hexadecimal will be considered for division. So you have to continuously divide that with 16, okay, until it is no more divisible by 16. So 472 divided by 16. What do we get? 472 divided by 16, 16, 2, and then it will be 9, right? And what we get as the remainder is nothing but remainder is nothing but 8. Correct. Then again we have to divide by 16. 16. So divisible only once. And the remainder here is nothing but difference between, okay, that is 13. Yeah. So again, that is the bottom to top approach. Okay. So we have to represent like what it is 0 to 9 we are considering or using the digits as it is. So from 10 it will be like we are going to use or to represent that we are using what we are using the alphabets. 10 is A or 11 is B, okay, like that. 12 is C, 13 is D, okay, and till 15 only we have. So totally this has the base of 16, so 0 to 15, that's what we are considering. So 14 is E and the 15 is F. So that is nothing but 1D8. Okay. And then the next one from hexadecimal to decimal. So again we have to consider the base for multiplication. So I'll consider the same how this can be done. Like 1D8 need to be converted to the decimal. So 1D8 need to be converted to the decimal. So that is the hexadecimal digit 0, hexadecimal digit 1, and the hexadecimal digit 2. Their positions I am telling. Okay. Then we have to consider the digit, the position of the digit also. So 1 into 16 power 2 plus D is nothing but 13. So 13 into 16 power 1 plus 8 into 16 power 0. Okay, so when we sum this up, surely what we get will be 472 itself. Yeah. Okay. So that is the conversion to the hexadecimal, hexadecimal to decimal, and the decimal to hexadecimal. So that is done. So next what we have is nothing but binary to octal, octal to binary. Okay, so binary to octal and octal to binary, it's actually easy. From the binary, conversion is actually easy. So, so here the maximum, like in the octal number system, the maximum is nothing but what we are considering as the maximum, that is 7. Okay, from 0 to 7 only digits we are considering as the maximum. Okay, so 0 to 7, the base is nothing but 8. Now what it is, this 7, what is the binary representation of 7? The binary representation of 7 is nothing but 111. Okay, which means we can use a maximum of 3 bits to represent a binary an octal number. Okay, so maximum of 3 bits is only required to represent one octal number, or each digit of our octal number. Okay, so what we can do, if we have a binary number somewhat like this, so I'll randomly take one 0 1 1 0 1 1 0 1 1 0 0 1 1 0 1 0. Okay, so I'm considering like this. So now what we have to do in the sense, we have to separate or divide this for every 3 bits. We have to separate every 3 bits. So from the right hand side you have to start. Okay, from the bit 0 you have to start. So bit in the sense binary digit. Okay, so we have to group it is 3 3. Okay, 3 digits are grouped. Now we have to find which is the equivalent octal number. So which is this one? 0 1 0 is nothing but 2. Then 0 1 1 is nothing but 3. Okay, 1 1 0 is nothing but 6. Then again 1 1 0, again 1 1 0, and then this is 0. Okay, just one bit is there, that is 0 itself. Okay, so the equivalent is nothing but 0 6 6 6 3 2. Okay, that's the equivalent of this particular binary number. Okay, now from octal to binary. So is this clear for you? Binary to octal. Till here, is there any doubt? Okay, is that clear for everyone? Okay. So I'll randomly take one octal number. Okay, so let it be 7502156. Okay, so I'm taking a octal number. Now what you have to do, you have to represent each and every digit in octal in 3 bits. Okay, so you have to represent each the bit of this particular octal number with 3 bits. So this will be like 7 is 111, 5 is 101. Yeah, then 0 is nothing but 0 also should be represented in 3 bits, 000. Then 2 is nothing but 010, 1 is nothing but 001, 5 is nothing but 101, 6 is nothing but 110. Yeah. Okay, so we have what we have with us nothing but the binary representation of this octal number. Okay, it's simple, isn't it? So similarly, we have one more set of not one more, I think. Yeah. So we have binary to hexadecimal, hexadecimal to binary. Then we have these two also. We will see. So binary to hexadecimal. So that's also similar to the binary to octal conversion. So which means the maximum, like the base here is 16. So we are going to take the numbers from 0 to 15. Okay. This 15, how will we represent the 15 in binary? 15 in binary can be represented using maximum of 4 bits, 1111, isn't it? So this is what we are considering, the maximum number of bits for any any hexadecimal digit representation. How we are mentioning binary to particular number. How we are mentioning, like how, which means when we take it into the system, how we are telling the this is hexadecimal or this is the octal. Are you asking that? Binary to a particular number, this is for our understanding. Okay, how this can be given in the system or where it will come, I'll tell you. For a particular number, mm, mentioning, I didn't get your question properly. So see, like, are you asking like how can we represent any number, any particular number in binary? Okay, any number in the sense, again, it matters whether it's an octal number or hexadecimal number or decimal number. Okay, so like usually what we are considering is decimal number for our all the operations, everything, like we will take only, consider only decimal number. The same number can be represented as octal or hexadecimal too. So it matters from where the number conversion should happen, whether it's the hexadecimal or octal or decimal. So always that will be considered for the conversion. 010 means 2, correct. Okay, I hope you know these representations, binary representation. Okay, starting from 000, then adding 1 to it. Okay, so you will get 001. Then adding 1 to it, you will get 010. Okay, I hope everyone knows this. These are the very simple basics. At least you should know this. Okay, I hope everyone knows this. Okay, that's why I didn't tell it specifically. So these things at least have to represent till the 15 in binary. That you should know. Okay, 8421 didn't get you. Okay, anyways. So what we are going to do, we are going to convert one binary number to. Okay, yeah, Ankit, are you telling how to multiply that? Okay, 2 power series. Okay, good. Anyways, binary. So I'll randomly take one binary number. Okay, 10 10 11 00 10 11 01 Okay. So this is the binary number I'm considering. I want to convert this to the hexadecimal. So I have to separate that as group of 4 bits. Okay. Now I have to represent that. So usually when it's a binary number and any operation on the binary numbers, we will start from the right hand side, which means from this particular bit. Okay, always it will be like that. That's why I'm writing from here itself. So 0100. Yeah, what is the equivalent representation in hexadecimal? So the digits that we are using is 0 to 9 and A to F. Okay, so using that we have to represent it. So 0100, that is 4. 1101, what is 1101? That is 13 and that is D. Okay. Then okay, so 1011, that is 11. 1011 is 11, so that is B. B. And then 0010, that is 2. Then 1011 again, that's B. And then 10. So that is nothing but 0010 itself. So that is 2. So 2B D4. Okay. So that is the equivalent hexadecimal. And similarly, So we have to convert it back to the binary as well. So that's like hexadecimal to binary. So I'll take one random number. So let it be like 1AD5, then F40B1. Okay, so this is the number which I'm considering for conversion. So this is the hexadecimal number. Now each of this hexadecimal digit you have to just convert to binary, that too in 4 bits. Okay, so that is what required. So it will be like 1 represented in hexadecimal, that is 0001. Now A is nothing but 1010. Dividing by 16, that is like when converting back to the or conversion from the decimal to hexadecimal is where we are dividing by 16. Okay, decimal to hexadecimal. So this is one another number system, hexadecimal to binary. Okay, the division and multiplication comes only for from the decimal or to decimal. To decimal always that is the multiplication with the base. Okay, base power. Then dividing by the base that comes from the decimal. From decimal to one another number system. Okay, that number system's base will be considered for division. Okay, and here that is the hexadecimal and binary. So there is no multiplication, division and all. So representation in the particular number of bits. Okay. Okay, we will continue with this. A is nothing but 0010. D is nothing but 1101. 5 is 0101. Then F is 1111. Then 4 is 0100. 0 is 0000. B is nothing but 1011. Then 10001. Okay, so that is the equivalent binary representation. So 1AD, D is nothing but 1101, then 5 F40B1. Correct. Okay, so did you get it? How can we do the hexadecimal to binary, binary to hexadecimal? So if you have the binary representation, then it's easy to convert to octal or hexadecimal. Okay, now one more type of conversion is there, that is nothing but from octal to hexadecimal and hexadecimal to octal. So remember always there is no direct conversion from octal to hexadecimal and hexadecimal to octal. So we have to convert either to the decimal or to the binary. Okay. So I told if the binary is there, it's easy to convert. So whichever is the number, if that's the octal number or the hexadecimal number, first we will convert that to the binary. So octal to hexadecimal. So here possibilities are nothing but we can convert like one method from octal to binary, then binary to hexadecimal. Or we can even do octal to decimal and then decimal to hexadecimal. So that's our choice. Okay, we can go with one of this. So I'll choose the first one because that is comparatively easy. Octal to binary, then binary to hexadecimal. So I'll consider one number, octal number. So let it be something like 752104. So this is the number which I'm considering for conversion from the octal. So octal number is here. First I'm converting that to the binary. So representing each digit in 3 bits. So 111, 101, 101, then that is 2. So 010, then 1 is 001, 000, 100. Okay. Now what we have to do, we have to take all these bits and we have to group that to the group of 4. Okay. And now we have to write the equivalent hexadecimal digit. So 11 is nothing but 3, then 1101. What is 1101? 1101 is nothing but D. Okay. So that is D, then 0100, that is 4, then again 4, again 4. Okay. So that is nothing but the equivalent representation of this particular octal number. Similarly, we can convert to from hexadecimal to octal also, we can do it in the similar manner. So that's the last conversion. So there also we have the option to convert it to the decimal, from there to octal, or to convert to the binary. So I'll go with the binary conversion, from there to the octal representation. So I'll go with one hexadecimal number, that is 1. So that is, let it be 1 second, 1F2C, then I'll go with 5D8. So this is the hexadecimal number which I am considering. Now you have to convert this to the binary first. So every digit should be represented in 4 bits. 11, then 0010. C is nothing but 1100, then 0101, and D is nothing but 1101, and 8 is 1000. So now again we have to group this as the group of 3 bits. So why? Because octal number is with the maximum of 3 bits in it. So 3. Sorry for that. Okay, so what we get here as the output answer. So that's nothing but 0, 1, 7. So 0, 1, 7. Okay, I'll write like this: 0, 1, 7, 4, 5, 4, 2, 7, 3, 0. Okay. So that is the octal number of this equivalent hexadecimal. So is the conversion methods clear for everyone? So if we have the binary, conversion to the octal or hexadecimal is easy. Okay. So is this much clear for everyone? Yes or no? So I'll give the classworks for this one I'll share that in LMS. Okay. Now how the data will be represented, like before that, I'll just go through the slide. The same things are there. So I'll come to this one. Okay, so we have to see this. So the different number systems and which are they, the range channel we will see now. Okay, then the similar examples are there as well. Go through it. Okay, some we have already done in class. Okay, so go through it. All the conversion methods are there as well. Okay. Now the data representation. So I told binary digit, in short, that is called the bit. Okay. So our systems, okay, so whatever data we store in our system, okay, like suppose if I want to store the character A, okay, this is what I want to store. So our systems cannot store it directly as A itself, okay, as the character A itself, it cannot store. So what is in fact happening there? It can store only as 0 or 1. In the binary form only, the data, every data, whichever it is, like it can be a number, it can be a name, it can be just one character, any character, okay? So a symbol, that's also a character. So anything, whatever it is, that is or non-integer numbers. So everything will be converted to the binary value and then only it is getting stored inside the computer's memory. Okay, either in 0 or 1, that is getting represented. Okay, so now we will see what is this bit and what it is, or the binary digit, how many binary digits we can access together and all. So the least or the smallest units that can be accessed in a computer's memory is nothing but 1 byte. Okay, the least memory that we can access. Okay, least memory is nothing but 1 byte. So what is this 1 byte? 8 bits together is known as 1 byte. Okay, so we can't access beyond that. Maximum, or sorry, the least is nothing but the 1 byte. So in 1 byte, or what is this 1 byte in the sense? 8 bits together. Okay, we can't get one bit. Okay, accessing one bit is, like, I'm not telling completely impossible. So is there any possibility? That we'll check later. So this is how usually the systems, or the whatever is there. So wherever we are going to store the data, okay, it will be getting stored in minimum of 1 byte. So like this, the data is getting stored in, this is in fact the 1 byte. So everything here is one bit, okay, 4 bits, and half of 1 byte is known as the nibble, which means 4 bits together, it's called as nibble. Okay, half of a byte. Nibble. Okay, but we can't access the nibble alone. Like we can't access 4 bytes separately. Okay, which means inside the system's memory, like whenever, suppose if that's a variable, getting the space inside the memory. So at least in 1 byte only it can get the space. At least 1 byte should be there. Okay, so whenever anything gets the memory, it will be at some address. So the address is only for at least 1 byte of data. Okay, address can be given only for at least 1 byte of data. That's why there is no separate addresses for the bits. Okay, bits are a part of 1 byte. So there is no separate addresses for the bits. we can access at least one byte only at a time. Okay, so not at a time. Like minimal unit is nothing but 1 byte. Beyond that, we cannot access it separately. The bits cannot be accessed, or we cannot get the address of the bits separately. Okay, that's the reason the least memory that can be accessed is always 1 byte. Okay, so in this 1 byte or in 8 bits, what is the least number that can be represented, or what is the least number that can be stored? Okay, least number in 1 byte. Okay, what is that one? What is that number? Or least number in 8 bits. What is that number? All zeros, isn't it? So 8 zeros together, the least one. Okay, I'm telling like this. In this 8 bits, if I store 0, 0, okay, so this is the least one what I can store in, or the least number what I can store in 1 byte. And this is nothing but in decimal, that is nothing but 0. Okay. And when it comes to the like the maximum number that I can store in 1 byte is nothing but it will be all ones, isn't it? So in place of all the zeros, if I keep all ones, okay, then what is that number? So here you have to go with binary to decimal conversion. So convert it to the decimal and tell me which is that number. Which is that number? 255. Okay, right. So that is what it is. Maximum is nothing but all ones together. So 8 bits are getting stored with ones. So that number in decimal is nothing but 255, which means in decimal what we can store? In decimal, okay, the range of the values is nothing but okay, the minimum is nothing but 0 and the maximum is nothing but 255. Okay, so the maximum number which I can store, a decimal value which I can store in 1 byte is 255. Okay, then what it is, you can just consider that in other number systems. So range in like a range in octal number system. Okay, so range in octal, what it will be? So 0 is nothing but, so understand the octal numbers, how it will be represented, or every octal number will start with a 0. So if you want to represent the 0 in octal, it will be 0, 0. Okay, 0, 0, 2. Now you have to convert this 255 to octal. What is the equivalent 255 of the equivalent of 255 in octal? That is 377. Correct. So every octal will start with a 0. So 0377 is the range of this particular what octal number what I can store in 1 byte. Okay. Now when it comes to the hexadecimal. So when we have the octal, the conversion to the hexadecimal is easy. Okay, 377. So 377. Now we have to convert that to okay, or what it is, all ones. The binary is already here. Okay, so when you have the binary, okay, that is easy. So the hexadecimal numbers, how they are represented in the sense, starting with the 0x. Okay, 0x, that shows that number is hexadecimal number. So 0x0 is nothing but the representation of 0 itself. 0x02, 0x and all one. So 0x and 4 bits together. Okay, 4 bits together, that is FF Okay, 4 bits. Each like 4 bits together, that is F. Then the other 4 bits together, that is another F. So like that, the maximum what we can store is nothing but 0xFF. Okay. So that is the range of the values or the equivalent values. So this is, so when that is the binary, okay, so I can even say range in binary that is already given here, even though the binary values, how it will be represented. So that starts with the 0B. Okay, 0B shows that that's a binary number. Okay, 0B 00000000 to 0B 11111111. Okay, so these are the ranges of the values in different number system that can be stored in 1 byte. Okay, is that clear for you? So if I say, suppose if I want to store, if I want to write in my program, for example, if I want to assign or I want to store 125 in a variable num. Okay, in decimal I can give it as 125. And in binary, if I want to store like directly, I'm giving that in binary. So 125 in binary, we have already seen that, isn't it? 125 in binary is 11111101. Okay, so that is 0B111101. Okay, again, if I want to store that in octal, so binary is already here, octal is 571. So 0175, 175. Okay, that is the octal. Then if that is hexadecimal, then that is like 1101 and 7. So that is 70. So 0x7D. Okay. So this is how we can directly store or directly give 0B to show that that is a binary number. Okay, like the first 0 here that shows that's an octal number. The system will understand by seeing 0B. The system will understand that's a binary number. How it is 175. You have to separate for 3 bits. 5, 7, 1. If the binary is there, conversion from binary to octal is easy. Okay, so 5, 7, 1. Isn't it right? So are you getting properly, correctly? Is this much clear for you? Okay, so these are the ranges, and this is how like the range of values that can be stored. Now, while coming to the character, so this is how the numbers can get stored, or again, then beyond 255, what to be done, we will see. Okay, that let it be later. So the now the thing is like if there is a character to be stored, okay, if I want to store a character, suppose if that is the character array, okay, how to store it in like this, how to store that inside the variable. So directly when I'm telling, so for example, I want to store that inside a variable ch. I want to store the character, okay. So to tell the compiler that it's a character, always we have to give that inside the double quote. Sorry, single quote. And note the double quote. Double quote has a different meaning. So that is used for strings. What is string and all we will see later. As of now, understand. If you want to tell the compiler, this is a character. Okay, so that it won't get confused whether it's a name of another variable or not. Okay, so like that also you can assign value to another variable. One variable's value can be stored inside another variable. That's also possible. So we are telling the compiler by giving the single quote that this is a character to get stored. So when I am trying to store like this, okay, how it is again getting stored inside the memory as zeros or ones only. Okay, only a 0 or 1 it's going to get stored. Okay, now the thing is like space doesn't matter here, which means this space, or did you mean the space before and after the equal to? No, it doesn't matter. You have to give the space here. Okay, even if you miss the space, it won't end up in error. Okay, so the usual practice is that to give the space. Okay, so what it is, if I want to store this character A inside the memory, so how this will be stored as zeros and ones. Okay, so that should be stored according to some standard, isn't it? So to store any character, like we are going to use 1 byte, okay, to store any character. What we are going to use in the sense 1 byte, which means like maximum of 0 to 255, which means a combination of 256. Okay, 256 combinations of zeros and ones are there to store the characters. Okay, printable characters, or where it is what all non-printable characters are also there, like the space. Okay, the space, yeah, up to a limit we can say that is getting printed. So anyways, like even though the space, like it's a one character getting printed, even though that's considered as like not like the character A and all. If that's alone, if the space character is alone, that is like it cannot be identified, isn't it? So that's also consider coming under the non-printable character. We won't get to see if that is one character getting printed. Okay, that's the thing. So where all these are the character codes. So there should be one standard representation for the A. Okay, similarly for all the characters, whatever we have, even for the question mark or even for at the rate, even for hash, for every character, okay, that we you see on the keyboard, for each and everything, there should be an equivalent standard character code. Okay. So these character code here, this character code depends on like which one is followed by our system. That depends on the system design. So I can say that depends on the JCC here. Okay. Okay. So there are different possibilities. So which one we are following is nothing but the ASCII equivalent or the ASCII character codes only. So that is nothing but the American Standard Code for information interchange. So it uses only 7 bits. Okay, it uses only 7 bits. That's why, which means out of the 8 bits in 1 byte, it's using only 7 bits. And there is an extended ASCII character code, another version of ASCII itself that uses 8 bits. But the common one which is being used is nothing but the ASCII, which uses only 7 bits. Okay. Then there are other standards also like EBCDIC, that is Extended BCD Interchange Code. Okay, Extended BCD Interchange Code that uses 8 bits. Okay. Then Unicode, that is a universal code, it uses 16 bits and more. So you can see the difference in number of bits used. This uses 16 bits and more, okay, like to store one character. Okay, so that is like more memory is required. This uses 8 bits, okay, that also comparatively one more bit is required, but fine, it uses only 1 byte to store one character. But nowadays, EBCDIC is not necessary at all. For all the printable characters, ASCII, which utilizes only 7 bits, is in fact used. Okay. So ASCII is like ASCII character codes are efficient ones. Like efficiently, we can use it. It uses lesser space. That's the advantage of this one. So 7 bits in the sense maximum, the least value in using the 7 bits. Okay, so 7 bits, the least value is nothing but 00000000. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay, so that too 7 bits. So that too 11111111. Okay, so these are the values, minimum and maximum values with which we can store the character codes, or where we have the character codes. Okay, so can you say like what are these values? Okay, which means every character code will be having a value within this range. Okay, in ASCII equivalent character code, every character will be having an equivalent decimal value starting from 0 to this particular one. What is this value? 7 ones, that is 127. Okay, so the maximum value for an ASCII code character code is nothing but 127. So now the thing is like, where can we see all these? Okay, so where can we see all the ASCII character code representation? For that, you have to go with the ASCII man page. Let it be up. So what I'm using right now here is nothing but the WSL. I'm using Windows. In Windows, I have the WSL. That's what I'm using. Okay, you can check it anywhere. So taking time. Okay, let it be up. Okay, see, we will see that. Now, I told the character will be stored as within the single quote only we are going to give the character code. So remember, even the like suppose if I have a variable num is getting assigned with 0. Okay, so if I give 0 to this one, okay, like this will be considered as, okay, getting stored as an integer. Okay, getting stored as the integer. So this is how it will be considered. And suppose if I am storing like within the single quote, if I am doing like this, that actually means this is a character. Okay, character 0. On the ASCII table, even you can see the, one second. In ASCII, we have reduce combination. Okay, we have 127, totally 128 are there. Reduce come it no. For every character there is representation. So I'll show that. That means 1 byte is not required for a single character. No, 1 byte is not completely used. Only 7 bits are used. So if you are using the Linux or Ubuntu, then you can go with the command man. Command man is to get the man page of anything. Okay, so here I'm just giving ASCII. Taking so much time, don't know it. Okay, so this is the ASCII table. So here we can see starting from 0. So every character starting from the null character. So this is in fact known as the null character. Later on we will see this in a detailed manner. So in bracket you can see that is called as the null character. Okay, so in the parenthesis the name is also given. So what are the things? Everything is given here with the what exactly that means. Then the null holds the in equivalent decimal value 0 and the octal value 000, hexadecimal 00. Okay, like that you can see for all the characters, every character. Okay, so these are actually non-printable. Okay, they are, can see even the bell, backspace and all. So these are considered non-printable characters. Then space, then the exclamatory symbol. Okay, or we can even say that as the note. So here that is one character. So that's why I told exclamatory symbol. Then hash. Okay, all those things. Okay, so all these are characters only. Then you can see even the 0 to 9, they are there as characters. 0 to 9 as characters, don't think they are the integers. So 0 has an integer equivalent of, okay, 48. Okay, 0 is 48, which means the integer or the decimal equivalent of this character 0 is 48 and the character 9 is 57. So from 48 to 57 in the ASCII table, that is character 0 to character 9. Okay, where it's used, what's the use of this and all, we will see later. Then like that, for each and every character, there is a representation. Then you can see the lowercase character starting from 97 to 122. Okay, that is the range of lowercase characters, and the uppercase characters from 65 to 90. Okay, starting from the equivalent decimal value 65 to 90. That is the range of uppercase characters. Okay, so when you have the man page, like you can just check the man page and see all the 128 character codes. Okay, totally from 0 to 127, we have 128 character codes here. Just start the stops with 127. So starting from 0. Okay, so that's the thing. That's the ASCII table. So using the ASCII table only, we are in fact storing the or considering the values to be stored. So in fact, when I am storing like this, if I am storing within the single code, what the compiler will understand, it's like num getting, so it's equivalent as num getting stored with the character 0 is 48. Okay, the same value will be considered to be stored inside the memory. So this whatever character is there, suppose if I am storing the A, how it will get stored inside the system's memory in the sense that will be converted to the integer. Okay, that the equivalent in not I'm not saying converted to integer, equivalent integer value will be considered for the character code. So that is 65 in case of uppercase A. Okay, so 65 is getting stored inside the binary. That is what the that is how the character A is getting stored. Okay, so is this much clear for you? So that is how the characters are getting stored. Okay, one character, how it is getting stored. Maximum of 1 byte it will be utilizing to store one character, and equivalent ASCII value is considered. Okay, ASCII equivalent value is considered to store that particular character. So is this much clear for you? Yes or no? Others? Okay. So now the thing is like how the like what how the word or what is exactly word in the sense the word is nothing but the number of bytes, okay, the number of or the amount of data that can be fetched or processed at a time. Okay, that can be fetched or processed at a time. Okay, here is it out. So in ASCII 1 byte equals 7. No, 1 byte means that is always 8 bits only. Okay, in ASCII it uses only 7 bits out of the total 8 bits. Okay, so 1 byte, it is a standard. 1 byte means always 8 bits together. That is 1 byte. So out of this, the 7 bits only will be utilized to store the character. Okay, the ASCII code will be stored only using the 7 bits. Okay, so in the sense, no, totally every character is going to take 1 byte only. Okay, so every character is going to take only 1 byte. Okay, 1 byte. So I can say the character is going to get stored in 1 byte itself. Okay, so the 7 bits will be considered for storing the particular character code, and this will be kept as like 0 or 1. So what that means, we will come to that. Remaining 1 bit, what happens to that? We will come to that one. Okay, we will come to that point. So in 1 byte, if there is one data, like how to understand that and all, we will see. Okay. So it has a meaning actually. What is this value that has actually a meaning? Okay, we will come to that point. Extended, that is extended code. Extended code is different. ASCII extended code. I can say that is the advanced or the another version of the ASCII standard. Okay, so what we are using is this one itself, which is going to use only a maximum of 7 bits. Okay, what is that eighth bit means? In 1 byte, if a value is getting stored, what is that eighth bit means that we will see. Okay, so I will come to that point. How to get integer value of each character. You have to see the ASCII man page. Okay, the ASCII is a standard. Okay, so you have to check the ASCII table to know what is the character or the integer decimal equivalent of each and every character. Okay, so I have shown right now. So similarly, you can check that as well. Okay, so at least the ranges and all you should know, like what is the range of uppercase characters. ASCII values, you should have an idea. Anyways, when we work again and again with the different values and all, somewhat you will get the idea. Machine will understand that depends on which compiler you use and which system. So it depends on the system design. Okay. So in GCC, like the ASCII equivalents are considered as the character codes. So in today's world, majority of the systems will be using the character codes only. Sorry, ASCII codes only. How to remember the ASCII value? By practice. Okay, so by practice, you will get an idea like from which range to which range is the uppercase characters, or at least the character A, uppercase A, that has an ASCII value of 65, or the lowercase character lowercase A, okay, that has an ASCII equivalent of 97. So 97 to 122, that's the range of lowercase characters. Like this, you will get an idea. Like then 48 to 57, that's the range of the character 0 to 9. Okay, so different compiler will, that is what, okay, not every, there is no much difference nowadays. ASCII is considered as the standard character code. Okay, so in very rare cases the other one like BCD, like EBC, EBCDIC and all will be used. So nowadays it's not much in use, very rarely it will be used, maybe for some specific purpose and all. Why? Because they utilize more memory. Okay, the ASCII will utilize only less memory. That's why ASCII is always preferred over the other standards. So yes, man on ASCII if you are using Linux. So the ASCII is the efficient one which uses less space. That's why always ASCII is used to store the characters. Okay, did you get an idea? Is this much clear? Okay, so now we will see like what is the word size. So word size in the sense the amount of data that that your system can fetch or process at a time. So in fact, this actually means what is like usually we will say 64-bit system, 32-bit system and all. So what actually that means in the sense 64 bits or 8 bytes is the number of, or the amount of data it can be fetched or processed at a time. That is in fact showing the word size. Okay, 32 bits, bit in the sense again that's a 4 bytes. Okay, so that is the amount of data that can be fetched in a single shot or processed in a single shot. Okay, so that will be the maximum. Okay, maximum that will be like 4 bytes is what is the size of an integer. Okay, so when we come to the integer or how the integer is getting stored inside the system. So if it's a positive number, that is going to get stored in either 2 or 4 bytes. Okay, I'm not saying completely 4 bytes every time. So again, that depends on the system design or the compiler. So if that is GCC, then it's going to get stored in 4 bytes. Okay, so like maximum of 4 bytes I can say. Okay, maximum of 4 bytes, that is where the integer, one integer value is going to get stored. So if that is a positive value, Okay, so that if that's a positive value, then it will be getting stored as the binary equivalent. If that is 13, 13 in decimal, that is going to get converted to the binary, and that is getting stored in 32 bits. Okay, so we know that this one, the 13 is nothing but 1101. Okay. So 1101. So these are the last four bits. Okay, always I told the bits when it comes to the binary number system, always it starts from the right hand side, or that is nothing but the bit number 0. Okay, so this bit 0th bit, from there only every operation on the binary numbers will start and all. So we are storing in the last four bits the 1101, and rest of the bits are filled with 0. So the value is not changing. Okay, so that is how the 13 is getting stored inside 4 bytes, a maximum of 4 bytes. That is something but one positive integer getting stored in 4 bytes. Yes, for Turbo C it's 2 bytes. So that is why I told that is compiler dependent. Which compiler you use, it depends on that. The size of the integer depends on that. Okay, so we are following GCC, or we are using the GCC compiler. That's why I told it will be 4. So this is the case when that is a positive number. And when that's a negative number, what happens? It is going to get stored as the 2's complement. Now, do you know what's 2's complement? Okay, there is a doubt. So 32-bit processor means it can store only 4 bytes of data. 32-bit processor means it can fetch only 4 bytes of data at a time. Okay, fetching and processing. What is the amount of data it can fetch at a time, not storing. Okay, like in a single shot it can fetch only 4 bytes of data at a time. Okay, there will be data bus and address bus, isn't it? So data bus is used for what? To transfer the data. Address bus to transfer the address. So if to transfer one data, only 4 bytes can be transferred in a single shot. That's the meaning. Okay. So now coming to the negative number storage. So positive numbers or positive integers, it will get stored as it is. From user interface, it can fetch only 4 bytes. Yes, correct, Ranjit. So negative 13. So the number which I'm considering is negative 13. Okay, negative integer. So this is going to get stored as 2's complement. Okay, and do you have any idea what is 2's complement? How to get the 2's complement? So to get the 2's complement, first you have to get the 1's complement. So we will write the 32-bit representation of this 13. Yeah. So 0, 0, 0. Okay, so that is the 32-bit representation of 13. Okay, 13 is going to get, so first we have to consider the 13, then we have to get to the negative 13. So how it is getting stored inside the memory. So which means first we have to get the 1's complement of this one. Okay, 1's complement in the sense we are taking the complement of each and every bit here. Complement in the sense if that is 0, we have to represent that as 1. Okay, and if that is 1, we have to represent that with 0. So and 1 1 1 1 0 0 1 0. Okay, now we have to add 1 to this. So 1's complement is taken, we have to add 1 to it, plus 1. So that's again with all the zeros and 1. Okay, now what we get? Adding 1 to it. 0 plus 1, that will be 1 itself. So 1 1, then 0 0, rest all will be 1 1 1 1, like that it goes. Okay, so all this will be, and this will become 1. Okay, so this is how, so this is the ones complement. Yeah, ones complement is this one, and this is the twos complement. Okay, so in fact, this is getting stored as, or this is the 30, negative 30. Okay, so it's getting stored as the twos complement. That means that is the negative 13. So this is how the negative 13 will be getting stored inside the memory. So now how to find 5's complement. Why the 5's complement, Andrew? There is only 1's complement and 2's complement. Okay, so we are discussing how this is getting stored inside the memory. So the negative numbers will be getting stored as the 2's complement only, always. So first coming to the 1's complement and adding 1 to it, what we get is nothing but 2's complement. Now, when you see this particular value, okay, when you see this particular value with which the negative 13 is getting stored inside the memory, don't you think it has some other value? Okay, so when we can actually consider 5's complement, so see, the complement will be considered for the binary numbers only. Okay, the complement is usually considered for binary numbers. Okay, so this 13, how it is, so what we are going to see, like we know that the range of the value, what is getting stored or what can be getting stored inside the 1 byte. Okay, inside the 1 byte, maximum of up to 255 we can store. Okay, so 0 to 255 is what we can store. And what I have considered is nothing but 13. Okay, negative 13. So I'll just, instead of taking that, like 32 bits will be a very large number. If I have to calculate what exactly this number is, then that's a very large number. So in short, like for the easiness, I'm considering 1 byte of data. Like this last 1 byte I'm considering. Okay, last 1 byte, like I have to see exactly in 1 byte how this value is being stored. Okay, the negative 13, if it's getting stored in 1 byte, exactly as what value it is getting stored. So if I take the negative 13 in 1 byte, so this is like negative 13 in 4 bytes. Okay, so negative 13 in 1 byte. In 1 byte also I can store the negative 13. That is within the range. Okay, 13 in 1 byte, that is also within the range. So to see how it will get stored, the negative 13 in 1 byte, first we have to consider the 13. Okay, so 13 is again 0000 1101. Okay, and what it is, similarly we have to go with the complement, one's complement, that is 11110010, and adding 1 to it. So what we get will be, okay, so what we get will be 1 1, so only here. Okay, so only for the last bit it will be changing. So 1 1, sorry, 1 1 1 1 0 0 1 1. Okay, now we have the value in 1 byte. Okay, now can you tell me what is the equivalent decimal value of this number? So this is in fact till the 0, yeah, till the 0. Okay, so this is negative 13 if I consider. Okay, so this is how the negative 13 is getting stored inside the memory. But this particular binary has an equivalent decimal value. Can you tell which is the decimal value? Decimal, not hexadecimal, decimal value. So you have to take each and every bit multiply that with 2 power the bit position. That is nothing but, so what into 2 power 0? Okay, 1 plus 2 plus 16 plus 32 plus 64. Okay, like that you have to do, plus 128. Okay, you have to see the bit position. So that is 243, correct. Okay, 243. So in fact, when that is like, when I'm storing, if I'm giving num is equal to negative 30. Okay, this is how I'm storing. So what the compiler do, if that is a negative number to be stored inside the memory, it will do the 2's complement. It will take the 2's complement, and that is what getting stored inside the memory. So this actual negative 13 is getting stored as, if you see, that is getting stored as 243 inside the memory. Okay. Then, or we can easily say, like suppose if I want to store a number as the negative number like k is a negative number. If so, that is like 2 power. So we can easily find in what, with what value finally it is going to get stored inside the memory. Okay, so that is going to get stored as 2 power n minus k. Okay, in this case, if I say that is like negative 13 is getting stored as, okay, 2 power n. What is this n in the sense? N will be 8 if that is getting stored in 1 byte. Okay, n will be 8, number of bits. That is what is meant by n. Okay, n, if 1 byte, that is 8. Okay, similarly, n will be mm, n will be 32 if that is 4 bytes. Okay, so if you want to get in 4 bytes, how, what is this value? You can accordingly, like 2 power 4 minus 13 you can do. Okay, so negative 13, how it is getting stored? 2 power 8, that is, okay, 2 power 8 is nothing but 256. 256 minus 13. Don't you get 243? Okay, so this is what we are getting. Okay. So always remember, if that's a negative number, it will get stored inside the memory as the like the 2's complement. Then while retrieving, like we knows that there is a negative 13 which is getting stored here. While retrieving, or when we take the value from the memory, how the compiler is understanding that is negative 13, that we will see later. Okay. So as of now, understand the compiler is going to convert this back to negative 13 itself. Okay, how it is considered as negative 13, that we will see later. Last bit. So yeah, actually that depends on this particular bit. Okay, fine. So is this much clear for everyone here? Yes or no? Okay. Then we have the, when we will take, okay, when we will take in the sense, see if the 13 has to get stored inside 1 byte. Okay, then this much is enough. If the, like it's like which way or which data type and all you choose. So to understand that, you have to wait till the data type. Okay, when we are going with 32 bits, when we are going with 1 byte. Okay, so as of now, understand the number 13 can be stored inside 4 bytes as well as 1 byte. Okay, that's within the range of 1 byte also. Okay, like up to 255 we can store in 1 byte. So it's possible to store the same in 4 bytes also. Okay, so when it will be used, or when it is going to take getting stored inside 4 bytes, that you for that you should understand the data type. Okay, so please wait till that. We will be seeing that soon. So now we know how the character is getting stored and how the integer is getting stored, the positive integer, negative integer. Even if that's 0, it's going to get stored in like either in 32, maximum of 32 bits. Okay, so then we have the non-integer values, something like 2.5. How will you store the 2.5? It's not like this. Okay, so it's not the 2's complement, it's not the direct conversion also. There is again another complex conversion method when it comes as the non-integer values. So from there we will see tomorrow. So we have to do the conversion. So that will take time. So after that only we will start with the data types. Okay. So is this much clear for everyone? Today's class. Is there any doubt? Negative 13 is a value. Yeah. Negative 13 is the integer negative 13. That, yeah, the value negative 13 as it is, it can be stored inside the memory. But how it will be stored as the zeros and ones only. Yes. Is that clear, Hari Krishnan? Like, do you still have any confusion? So others, if you have any doubt, you can ask the doubt. Else we'll wind up the session. How to choose? Yeah, that's what I told. How to store this same number in 1 byte or 4 byte? That depends on the type of this variable. Just now, I just told it's a variable. I didn't say it has a type and all. So for that, you have to wait till the next class. You should know like how it's given in the programming. Okay, so what we are going to do, how we are going to store each and every data. So there comes the importance of data type. Okay, what is your actual doubt, Anil? So all over what we were seeing here is nothing but how the data is getting stored inside the memory. So understand whichever data it is, whether it's a character or integer, non-integer, whatever it is, it's going to get stored inside the system's memory as zeros and ones. So if that's a character, we now know that's going to get stored in maximum of 1 byte, and in that 1 byte it is the like what it considers is nothing but 7 bits to store the equivalent ASCII equivalent character code. Okay, that each and every character will be having a character code. Every character code will be having an equivalent integer or octal or hexadecimal value. So that is getting converted to the binary. That is what being stored as 1 byte. So any character will get stored inside a maximum of 1 byte. Similarly, any integer, okay, any integer value that can be stored inside 4 bytes, a maximum of 4 bytes. Okay, so a maximum I'm telling of 4 bytes. So again, that depends on the range, whether it can be stored inside 1 byte or not. So a maximum of till 255, so 0 to 255 is what we can store inside 1 byte. A 1 byte means there are 8 bits. So maximum is nothing but 255. So this is what we have seen today, the different conversions and what is the data that can be stored inside the 1 byte and how the numbers are getting stored. If that's a positive number, direct conversion will happen. And if that's a like representation in binary and the like in 32 bits, it's going to get stored. Okay, maximum. And if that is a negative number, always it will be converted to the 2's complement of the positive number, and then only it will get stored inside the memory. Okay, so this is what we have seen today. Any doubt? Anyone? Till here, is that clear for you? Okay.